So good morning. I'll be heading for lunch right after my talk, I guess. So I've been working for the guys in the middle, as Ken referred to us in the example from the Athabasca Basin, for about a year now. And an interesting story about working in the Athabasca. We do a lot of work for the various companies that are dominant in that area. And each of those companies have their own bias in terms of the geophysical technologies they use for exploring for the same deposit model. So we do a lot of EM for one company, a lot of resistivity for another, and a lot of MT for the third. So we all are add our bias to these, to the way we explore. Quantec Geoscience in 1998 stepped out and recognized a need for technologies that sought a greater depth, and as a result developed systems that provide high volume and lower noise data sets for that use. And today I just wanted to talk about two data examples from these types of surveys. The first is a 2D Titan 24 survey in a brownfields application, and the second is a 3D Orion 3D survey, newer technology in a more greenfields application. So the first example is from Chemist North. It's in British Columbia, a deposit being mined, and it's really going through the life cycle of our involvement in the project, right from the initial synthetic modeling right through to the interpretation of the final results after the survey. So the objectives are to demonstrate the use of physical properties and the synthetic modeling to design an effective program. And then we're going to show the results from the survey that was ultimately carried out there. So I think it's important to note that we used existing data. We never want to throw away the old data. It's all very useful. So we used existing data to establish physical property measurements or physical property estimates for the various geologic units and mineralization on the property, and to generate synthetic models for survey design. And then we find that the final results agreed with the synthetic model, so it was a successful proof of what was planned. And in the end, of course, you want to have success in the drill holes. In this case, they had good success. So the Titan 24 distributed acquisition system was developed in 1998 by a contractor at great expense, a little unusual in that sense. I think about $5 million in investment. Oh, this is on auto advance. We lay out 24 or more inline dipoles. We put in cross-line dipoles every other one, so 12 of them. And then we transmit along the line, in and amongst those dipoles along the line. The rest of that are receivers. We collect DCIP and MT data. And so for that we need a magnetic station, and then we use a remote to support that MT acquisition. Press the wrong button and I'll shoot Ken over there. So this is just a section for a Titan 24 spread, typical 2.4 line kilometer length, get down to about 700 or 800 meters. And in the survey you can add extensions, current extensions off the end of the lines to extend your depth along the edges of the survey. And you can go with larger dipoles to affect greater coverage at the cost of resolution. So the survey objectives obviously is to find more ore in this case. It's a typical copper-gold porphyry target occurring at the surface in the Takla volcanic sequence. And but this host stratigraphy becomes progressively buried towards the east through block faulting, and significant throws on these faults. And the cover is younger volcanics and talus and in intrusions. Challenges in the area are rugged topography and contact issues. So Titan was selected as an appropriate technology for the depth requirements, and 2D synthetic modeling was carried out to gain confidence in the effectiveness of the survey and to sort of optimize the specific parameters for the survey. So we created 2D synthetic DCIP models for the deposit using pole-dipole data. We calculated the data, the synthetic data. And then we created these models both for the barren case and the mineralized case, so that we can ensure we could tell the difference between a lack of mineralization and a mineralization case. And then we created the 2D inversion models for both resistivity and chargeability, and then we did the comparison. So here, hard to see, I think, are the old data sets, contour maps of old dipole-dipole data and pole-dipole data. And from these data sets, we were able to reasonably accurately estimate the physical properties across the known mineralization at Chemis, south and north. So here we see the barren and mineralized geologic models that were developed and the physical properties, physical properties that were assigned. These are the typical resistivity and chargeability values for the various units. And then the mineralization has been split into the ore, which is the copper pyrite porphyry, and then the pyrite cap, which vary, but not by a whole lot. And you can see there's a significant contrast between both the pyrite cap and the ore and the host lithologies. So this is the resistivity model synthetic data. We produced sorry about that, I'm having trouble with these buttons. On the top there for the chargeability, and then this is the synthetic inversion result of the chargeability as well. So here we can see that there is good similarity between the data, so it recovered the data quite well, the synthetic and the inversion result. And the model itself is recovering very well the expected responses at the three depth levels for the cap and mineralized zones. So we're going to compare the barren versus the mineralized models. On the left, we have the barren forward and inversion results, and on the right, we have the mineralized forward and inversion results. So we can see a very good similarity between the forward and inverse models in both cases, but there is a marked difference between the barren and mineralized modeling that was completed. So it gave great confidence in the ability of the system to achieve what they wanted to achieve. And the same images for chargeability. Barren on the left, mineralized on the right. And in this case, you can see a very strong anomalous response where you have mineralized at the depths that they're interested in mapping to. So in summary, for the synthetic modeling, the parameters for the survey as defined, two 2.4 kilometer spreads, the 200 meter overlap for continuous coverage over fairly long distance. Was an appropriate approach to achieve the depths and resolution that they required. And we're confident in being able to see down to 300, 600, up to 300, 600 meters of the volcanic cover above the Takla. And as you can see, we're gained great confidence in the ability to detect the porphyry mineralization, both cap and the mineralization. There was not a lot of difference between the cap and mineralized zones, but that wasn't a critical aspect of the project in the mind of the client. So they decided to go ahead with the survey. Here's a view of the train. This is about a 4.8 kilometer long line extending across here. You can see the individual dipoles and then the cross lines as well. And we collected both DC resistivity, IP, and tensor MT. So we'll be looking at three of the lines that were completed. There were more lines completed through the survey area. This line is TA here. This line is TB, and this line is TC. So line TA, these are the 2D DCIP inversion results. You can see the data observed on the top, the calculator on the bottom, and the inversion models at the bottom for both the resistivity on the left and the chargeability on the right, so that you can see that we're mapping continuation of these known deposits, which are in the near surface, to the east and at depth, sort of the northeast and at depth. And as well, the chargeability is showing very strong responses to the northeast at depth. Okay, all these points. I'll flip over here. Line TA, these are the multi-parameter inversions. This is again chargeability, using both a null resistivity reference model and using the resistivity model as a starting. So again, just confirming the validity of the model response based on a varying starting model. And you can see that the responses of interest are consistently there. The information to depth does vary. So just for reference, ChemS North is the known mineralization. The Altus zone is a new discovery based on these results. And the Aura zone is a known mineralization. Now this is line TB, which again is southeast of line TA, shorter line, but running in the same direction as TA. Multi-parameter inversions, smooth 2D IP, and then the null resistivity reference model on the bottom. So showing this a good comparison and confidence in the results. This is line TC. This is a sort of a orthogonal line to TA and TB, and it really connects the two other lines. And across the Aura zone. The Aura zone is at the intersection or near the intersection of TB and TC. And you can see in this case, line TC is crossing that Aura zone in its entirety and maps it quite well. And it shows the extension of that zone to depth. So some GoCat images showing these inversions with ChemS North location as reference. all these are showing the extension of the zone to depth toward the northeast, and picking up all the known mineralization quite clearly. So these are some press releases that came out, I guess, from Northgate Minerals, who operate that area, and identifying the new targets that the survey had identified. And these are the new zones that they were quite interested in exploring: the new zone, the offset zone, and Chemes North. So some drilling was carried out. This is the existing pit area over the Chemes deposit, and this is the Aura zone, and then these are the new zones to depth. And then the exploration drilling hit on these zones identified through the Titan surveying. So success, really the ultimate success is what you get out of the holes, confirming extensions to their deposit across those faults in the Aura zone and the Altus zone. So findings, the field surveys corroborated the initial synthetic modeling, always very gratifying, and the ultimate gratification is the discovery of new mineralized zones, extensions of known mineralization. The inversion results suggest the deeper copper-rich zone is not differentiated from shallower pyrite halo, and the Chemes North and the Aura signatures are consistent with the previous geophysics, which is great to see. And the mineralized zones are defined below about 350 meters of cover, and extending down to about over a kilometer. I'm going to have to move on fairly quickly through this. Good to use available physical property data in setting up these types of surveys, and running through these synthetic modeling studies is always a good idea. De-risks and allows you to optimize your survey plan. Second example is, as I mentioned, a 3D survey. This is also in the Western Cordillera, but in Chile, over the Santa Cecilia deposit. Cerro Grande Exploration is the company. The survey was done last year. I'm going to go through these slides fairly quickly in the interest of time. You can see the terrain. The center of the system is at the top of that Cerro del Medio, at an elevation of 4,600 meters, and the bottom is about a kilometer below it. So challenging terrain. There is a history of geophysics through the area, but generally fairly shallow penetrating geophysics. I'm not going to go through this. Ground mag was done. We'll show a little bit of that. CSAMT, and then the Orion 3D survey. It's in the Maracunga mining belt, very close to the Caspiche development right now, and other mines in the area. This is the alteration package. The top of the mountain is right here, where the stock outcrops, and you got the different grades of alteration. The main center is here, and then you've got this sort of apophyse off to the southeast. Widespread silicification, as mapped. Again, we have the stock in the middle for reference. This is the ground mag that was completed prior to the survey. You can see the reduced pole is fairly benign. When you do a second vertical derivative, the alteration pops out quite nicely. You can draw all sorts of line. This is a 3D inversion of the mag, showing lows in the center and lows off to the east, southeast as well. CSAMT was done identifying a conductive feature underneath which was of great interest. They suspect it may be a porphyry, and on the strength of that CSAMT surveying, they did drill two deep holes, 1.4 and 1.7 kilometers in depth. They also had MMI data to support their decisions, copper, elevated copper and elevated gold over that conductive response. So in 2011, two holes were drilled down in to test this conductor, and they discovered mineralization, not spectacular grades, but confirming the porphyry system, down at a depth of about 250 meters, and extending really to the end of the holes. They never left the system, so a very large system. The CSAMT didn't tell that story. It was depth limited. The drill holes told a different story. So they needed a deeper penetrating system to understand what's really going on at those depths, and to get a better picture of the whole system. So in the fall of 2012, Orion 3D was selected and was surveyed. You can see the layout over a 3x5 kilometer block. There is a gap in the acquisition in this valley because of land access restrictions, but we just occupied both sides. And then the current injections, the MT data, MT stations were collected. Sorry, I'm going to go back. Across here, 110, a little over 100 MT sites. This is the pseudo volume plot of the resistivity data and the chargeability data, and then 3D inversions of the data set. So in the center, under the mountain, you've got about a 1.1 kilometer depth of penetration with the DC and chargeability data, and on the edges closer to 500 meters. As you can see, you're mapping the concentric nature of the system here. Taking a slice out of that volume, you can see some of the detail at depth. This is the chargeability response, mapping the near surface mineralization. Again, concentric mineralization around the edges, different phases of that system. And at depth, the chargeability response is maybe better shown through depth slicing. This is a horizontal slice, which is at 700 meters depth under the peak of the Cerro del Medio mountain. And you can see the resistivity is mapping a concentric circle around the stock and the intrusion, and some other concentric responses. And then some other interesting responses off to the east. The Caspice deposit sits just up in here. Those are the near-surface silicified veins. And you can see that in the chargeability response, you're getting good evidence of that in the near surface. But identifying some other large features of interest down in that extension of the zone. Going to greater depth, this is 900 meter depth slice. You're starting to lose coverage at the edges. But again, mapping that ring around the central stalk, and then some other concentric zones through here. And the chargeability at the 900 meter depth from the top of the mountain, we see some, again, some good mapping of the various phases within that system. This is the 3D MT model. This is the MT model, 3D inversion of the MT data of the 100 sites, and we'll just slice through that to take a look at what it says about the porphyry system. It's mapping that highly conductive porphyry from about 200 meters to about a 2 kilometer depth. So if we put the DC resistivity through a section and then add the MT to sort of extend that response to depth, we can see that this system is mapping that whole system, the top kilometer, in greater detail with the DC results. And then to depth, you're getting a good picture of what's going on with the full extent of that, of the porphyry system. So comparing it to the CSAMT that was done earlier, the CSAMT isosurface is sitting here. I think it's a 10 ohm meter isosurface. And then the MT is extending that, the knowledge of that system to greater depth and providing, maybe some glimpses into what's going on at great depth. Those are the drill holes. And an isosurface. And I think that was supposed to rotate. I forgot to mention that. So that's a picture of two surveys that Quantec's been involved in, one 2D, one 3D, really aimed at de-risking exploration. The view is that in both cases you can reduce your overall cost with effective application of new technologies. In the second case, they've only drilled 2 holes, and they didn't really know where to go next. They came in, spent a bit of money on a larger survey, and got the complete picture. So now they have a very good view on where they would best go next, and can optimize their next phase of exploration. These are data-rich surveys, and what we deliver is generally what Chris would refer to as lazy inversions, but they really are our first pass. And these data sets will live with and through the life of these projects. Usually these types of surveys are done in areas where there's value in the ground, and you're going to be exploring there for a while. So the data set will live and grow, and the models that are driven out of it will improve and add value for many years. Thanks very much.
Well, a couple of questions on the second properties that you were talking about. The Orion survey, those 15 square kilometers, what was the cost of that, and how long did it take to acquire?
Well, the cost of that particular survey we can't divulge, but a similar one that was done in the western U.S. Was all-in cost to the client, as they reported on their website, $500,000. And that was a slightly more detailed survey, but a similar area. So smaller dipole spacing, but a similar area.
Okay, and how long did it take to acquire?
The one in South America took about a month, between 3 and 4 weeks, I imagine. Yeah. It varies significantly depending on terrain, how much vegetation there is, access, of course. Mm-hmm. But generally, 3 to 4 weeks would be reasonable for that.
Well, I don't want to be hogging the mic, but a couple of other questions. Why was it so conductive? I mean, there not a lot of sulfides in that system, or was there a lot of pyrite in the system?
Yeah, I don't know the details of the geology, to be quite honest. So I can't answer that question with any certainty. Sorry.
Okay, I still have the mic. In both cases, it looked like the bodies of interest had flat-lying bases to them. Is that borne out by the drilling too, or is that potentially an artifact of the modeling?
Well, in the second case, they, being a junior mining company, have not been able to follow up yet. They are planning to do so this coming year. So, no, it hasn't been borne out by the drilling, other than the fact that the model did show that the drill holes should still be in mineralization at the bottom of the modeled response there. The chemists, I don't know. That's a good question. Don't know. Yeah.
Thanks, Mike. Just a quick one before we get into our next talk. It's more of an observation, but I say build on the point that the CSAMT survey there reminded me in a way of, I don't know if any of you were at Dan Wood's talk, but he was discussing down at Escondida, there's 2 existing pits, the Escondida and Escondida Norte. And between it was an area that they were planning to put tailings, and so they would do condemnation drilling. All the holes for the first campaign all went to 250 meters. Didn't hit anything. So it looked good. Then some twit drilled a hole that went, I think, to 600 or 700 meters. There's another deposit there. And I'm just thinking that maybe the people that thought of the CSAMT survey, not that they did a wrong thing, but they had a concept of how deep that they thought something might be. Maybe there was an economic criteria, maybe there was a geological one. But clearly there's a very interesting set of geology and geophysical responses that extend well below that CSAMT survey. So, your ideas are constrained by the data you have, but that doesn't necessarily mean that the world is constrained by those as well. It's all a cost balance. I mean, maybe they got that survey for 50,000 for a fraction, but they only got to see a peep of what was going on.
Yeah, I mean, the CSAMT got their drill into the right geology, and they found out, yeah, we got something here, and then they said, okay, well, now we got to look at the whole thing.
Right, exactly. Okay, thanks, Jonathan. We'll move on to Finn's first quantum.